All right, let's get started here with 4.3. And what we're doing here is monotonic functions. These are basically functions where on a range they're either always increasing or always decreasing, and then also our first derivative test. So let's look here and identify the function's local and absolute extreme values, if any, saying where they occur. All right, so for example, we can look right here and we see that this is the absolute highest point on this graph, and so therefore this is the global maximum, and it's occurring at the point, what do we have, -4 here, and then 2 on the y. So this is at -4, 2. So the maximum value is 2, and it occurs at x equals -4. So absolute max at x equals -4, and it has a value of 2. All right, so we have an absolute maximum of 2 that is occurring at x equals -4. All right, we can come along here and we see right here on both sides, if we were standing right there, either way we tried to walk, we'd be going uphill. That right there tells us this is a local, at least local, it might be global, but it's at least a local minimum. And since I can look over here and see other points all here that are all less than it, then it can't be the global minimum. So this is a local minimum. And just like before, it is occurring at a certain point, and that point is -2, 0. Okay, that's that point right there. In fact, I might move that just a little bit. That's at -2, 0. That's just not good. -2, I'll get it, -2, 0. There you go, that's that point right there. All right, as we come along, we see we reach a high point here where we don't go anywhere else. We know this is not the highest point on the graph, but I know that if you stand there, if you were standing right there, if you tried to walk right or left, you'd be headed downhill. Therefore, this is a maximum. It is not the global maximum. We already found the global maximum because there are all these points all over here that are higher than it. And so this is a local maximum, and it is occurring at the point 0, 1. So it has it's occurring at 0 and has a value of 1. We follow it along here. We go downhill, 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 and then suddenly we reach this point here. We're at a low point there. This is a local minimum, but it is also the global minimum. It is the lowest point on this entire graph, the global minimum, and it's occurring at x equals 2 and has a value of -3 there on y. So it's at the point 2, -3. Excuse me. And so then we also have to continue on over to here where we again reach the highest point. If we were standing right there, we can only walk one way. We can't walk right. We can only walk left, which would be downhill. Therefore, this is a maximum, and it's a local maximum because it's not the maximum point of the graph, and it occurs at x equals 4 and has a value of -1. Okay, so there we did. We found all the points, all the local and global maximum minimums of that graph. And so the next thing it asks us is, what is the derivative of these values? So if we went to all of these points outside of the, except the endpoints, right? Which was, this was an endpoint and this was an endpoint. Outside of the two endpoints, what is the derivative of these values? And the answer is, the derivative at those points is 0. Okay? So excluding endpoints. Okay? What is the graph doing between these values? Well, it's either increasing with positive slopes, or it's decreasing with negative slopes. Okay, so if I look at this graph up here, if I look at, say, here, let's pick another color. Let's pick purple or something. If I look between this point and this point, if I walk, if I walk along this path, I'm increasing the whole way. But if I look between this point here and this point down here, everywhere, all in between, I'm always decreasing in value. I'm walking downhill. Okay, so between all the points, I'm either walking uphill, in which case I have positive slopes, or I'm walking downhill, in which case I have negative slopes. All right, so let's see if we can use this sum. So example 1, find the critical points of f of x equals x cubed minus 12x minus 5, and identify the open intervals on which f is increasing and on which f is decreasing. So let's pretend we don't see this picture over here for the moment, right? We don't see that. That wasn't a very good scribble. Pretend we don't see that for a few minutes, and let's just work this out. So this is our function f of x right here. So to find the critical points, we need to find the derivative of it. X cubed becomes 3x squared, and 12x becomes a 12. And 5, when you take the derivative, it's a constant, it becomes a 0. We then need to plug in or set this equal to 0. So 0 equals 3x squared minus 12. At that point, we solve for x. We get 3x squared equals 12. And then we get x squared equals 4. And then x equals plus or minus the square root of 4, which is plus or minus 2. All right, so we took the square root of both sides, plus or minus that, because 2 squared is 4, and negative 2 squared is also 4. So both of those answers work. Now we need to figure out what the actual y value is. So we have the x value. Now we need the y value. So we plug those values back into our original function. So we start by plugging f of 2. That's 2 to the third minus 12 times 2 minus 5, like that. And you do that all out. 2 times 2 times 2 is 8. 8 minus 14 is negative 6. Is negative, hold on, that's not right. 2 times 2 is 4, times 2 is, this is 8 minus, 12 times 2, not 12. What did I do? Is 8 minus 24 minus 5. Sorry, I'm just can't do 2 times 12 apparently. I said that was 14. It's 24. And so this is negative 21. There we go. So there's one of our points. The other one, we can plug in the negative 2 value, and we get negative 2 cubed minus 12 times negative 2 minus 5. That gives us a negative 8 plus a 24 minus a 5, and that's going to give us an 11. All right, and so our critical points are 2, negative 21, and negative 2, 11. All right, just like that, those are our 2 critical points. Now notice this is an open interval, so we don't have to worry about looking at the endpoints, right? Because this, now we can actually go up here and look at our graph. So we look at this graph, we see right here, here's the point negative 2, 11, here's the point 2, 12. Those are clearly local minimums or maximums, right? If you were standing right here and you tried to walk in either direction, you'd end up going downhill, so that's a maximum. If you were standing right here and you tried to walk in either direction, you'd be going uphill. That therefore is definitely a minimum value. All right, so now if we look at this graph, we remember that this, let me get blue here, this is continuing on and this is continuing on to infinity, so we don't have to worry about those. for being those. So we don't. So these are most definitely just local minimums and maximums, so we don't have to worry about that. Now what we have to do is figure out, is it increasing or decreasing? So again, we're going to ignore that graph for a minute, and what we want to do is essentially look on either side of the functions and in between, or not either side of the function, either side of the critical points and between the critical points, and just see what kind of slopes do we get. So if we're looking at the interval from negative infinity all the way up to -2, right? That's this point right here, or up to that point right there. We can just do a quick little derivative and plug in a value that is less than -2. So we can do any one you want, f prime. I'm going to pick -3. You could pick -4 or -100 or -1,000,000, as long as you don't cross another critical point. Then you're okay. And because the critical points are going to be everywhere where your sign change, where is the only places where your sign of your derivative can change. So as long as we don't cross a critical point, we're good. We just need something to the left of it. And if you plug this -3 in, it becomes 3 times -3 squared minus 12. And -3 squared is 9. 9 times 3 is 27. 27 minus 12 is 15. And this is a positive number. It's therefore a positive slope. And if we have a positive slope, that means we are increasing. Therefore, increasing on that interval. So if we come look over here on the graph, we'll look at it again for a moment. If we split this right here, this is the interval we're looking at from negative infinity up to -2. And over that part, it's increasing like that. We're going up the entire time. It's all positive slopes. So now let's take a look between our two critical points. So we need to be between -2 and 2. Okay, so we'll pick something in there. Something easy is probably 0. 0 is between them. And since these are our two consecutive critical points, all the slopes have to have the same sign, all either positive or negative. So we plug in 0, pick any one you want. So pick something easy, and then go ahead and do it. You've got 3 times 0 squared minus 12. So that's just minus 12. This is a negative slope. That means all of the slopes between those 2 points are negative, and therefore the function is decreasing on that interval. If we look at that interval here right now, that's between these 2 points here, and everywhere in there you can see it's all downhill, it's all decreasing. Lastly, we need to check to the right of our furthest to the right point there, which is 2, -21. So we need to check to the right of that point. So we pick any point, any number we want. So I'm just going to go with 3. 3 is greater than 2, so that's to the right of it. So the derivative function evaluated at 3 is going to be 3 times 3 squared minus 12. So 3 squared is 9, times 3 is 27, and 27 minus 12 is, again, 15. So there you go. We ended up with 15 there as our slope. It is positive. It's a positive slope, and therefore we have an increasing function on that interval. And if you look on this interval, it goes out to infinity. We are increasing the entire way. So every tangent line you could draw in on that side is all going to be positive sloped. Okay? So hopefully that makes some sense. And you could maybe start to see how we could use this information. Say we didn't, if we didn't have this graph, it wasn't given to us, we couldn't look at it to check, but you could kind of see how we could maybe use this to come up with the graph ourselves, where we could mark our two critical points, right? And we'd say, okay, here are our two critical points at -2, 11, -2, 11, and 2, -21, and we could mark these points, and then we could go through and we could say, well, we know over here, we don't know exactly what the shape is, we know this has to be smooth and continuous, we know it's increasing over here, we know it's decreasing between them, and we know it's increasing over here. So this gives us at least some idea that it's increasing the whole way on that side, and then you just kind of connect it with a smooth curve, and it's not going to necessarily be perfect. Maybe if you added in finding like some x-intercepts and y-intercepts and stuff like that, you could get this graphed pretty well. You have all the major features just based on what we did mathematically to come up with a picture that looks pretty close to that right there. You at least get the general shape, and you can kind of figure out what kind of a graph you have using this. So pay attention to that. It's going to be pretty important for us going forward, because you can use it. So let's take a look now at the first derivative test. Essentially, we just did that. We just looked on either side of critical points and saw whether or not the derivative was positive or negative. If we found on one side of it that the derivative was positive and we didn't cross over any other critical points, then we knew that everywhere in between, if it was a positive slope for one point, it was positive for all of them, because the only way you can change slope is to move through a critical point. And so if we look here, here are some critical points right there and right there, and right here is a critical point. This isn't really a critical point here, this one, because it's not a derivative of 0, but it is an absolute maximum. We have a bit of an undefined slope at that point, so you'd have to take a look at that point as well to see if it happens to be a maximum or not. And of course what happens on either side of it. So you kind of have to look at those as well. So you want to look at points where we have an undefined slope and points where we have undefined, or where we have slopes of 0. All right, those are the places you're going to especially want to look. Okay, so let's take a look here. At the points F has a minimum value, m. So minimum value, that really only happens for us right here. This one minimum value here, let me change colors, that happens right here. To the left of m, all right, to the left of this value, this is m, this is our point m. To the left of it, over here, we have all negative slopes, all right? The derivative then is going to be negative, okay? F prime is going to be negative. To the right of that point over here, look at this, we have all positives, so it's all uphill. That means F prime for any one of those points is going to be positive, okay? Finish writing that. At the point F has a maximum value, m, right? If it's a maximum value, we're going to have, like, so say we looked at, let's get a different color here. Let's say we look at this maximum point right here. Everything to the left of it, we have a positive slope. So to the left, we can look at this point m, a capital M, right? Instead of that lowercase m. Everything to the left of it, F prime, is going to be positive. And everything to the right, F prime, will be negative, which you can see right here. So to the left, all positive. To the right, all negative, going downhill. And so again, like I just talked about with that last example, this would be a very good way to determine and find all your local and even some global extrema. So let's look here. So this is our first derivative test. Suppose that C is a critical point of a continuous function f, and that f is differentiable at every point in some interval containing C, except possibly at C itself. Moving across C from left to right, if f prime changes from negative to positive, that's going to be, so we're going from left to right, so this is this example, from negative to positive at C, then we have a local minimum. That's right here. We're going left to right, so we're going from negative to positive. That's what's occurring at a minimum. We're coming here from the left. Maybe I do need another color. We're coming from the left, we're at negative, and then suddenly we cross that point and we go to positive. That makes that a minimum. Okay, that's all that's saying to us. Part 2 tells us if it changes from positive to negative at C, that's like this point up here. We're going positive slopes, right, over to negative slopes. That gives us a maximum. All right, that gives us a local maximum. If f does not change signs at C, that is f is positive for both c, that f is positive on both sides of c or negative on both sides of c, then f has no local extremum there. So take a look, for example, at, I don't know, we'll go with gray, I guess. So here I have a positive slope, and then I cross this where I get a zero slope, but look, it goes back to being a positive slope. So you notice this point right there, while it's a critical point, is not an extreme value. It's not a maximum or a minimum. All right, that's what that is. And that's that example there. It's also this one over here. We have a negative slope right there, and after we cross that critical point, we go back to having, or continue having, a negative slope. Really go back to, because I guess at the critical point we didn't have a negative slope. So number 3 means that critical point does not necessarily mean it's an extrema. Okay, it's not an extreme value necessarily. It might be, but it also might not be. Okay, so you have to pay attention to what happens to the slope on either side of a critical point to tell you. All right, let's take a look at this example. So I'll do this example and leave the next 2 for you to try on your own. So let's take a look at A. It tells us to do find the critical points of this function. And so this is our function here. That means we have to take the derivative of it, f prime of x. Here we have 2 functions. X to the 1/3 is the first one. X minus 4 is the second one. So we can do a chain rule a product rule to get this. If you really wanted, I guess you could distribute that through the x to the 1/3 through and do it just another way, but this is pretty quick. So derivative of the first one is 1/3 x to the negative 2/3 times the second one, which is x minus 4, plus the first function, x to the 1/3, times the derivative of the second one. Well, the derivative of x is 1, and the derivative of 4 is 0, so it's just a 1. And so we can take this and make this x minus 4 over 3 times x to the negative 2/3 plus x to the 1/3. Now, in order to solve this, we need to set this, or to find our critical points, we need to set this equal to 0. By doing that, we get x minus 4 over 3x to the negative 2/3 equals negative x to the 1/3. Okay, and then what we can do is go ahead and multiply both sides by that 3x. Oops, this should have actually become a positive right there when I moved it to the denominator. Multiply both sides by 3x to the 2/3. We get x minus 4 equals, and so over here, what we end up with is negative 3x, because x to the 2/3 times x to the 1/3 is just x to the 1. It's x to the 3/3. And so then, based on that, we can add 3x to both sides and add 4 to both sides. And so x plus 3x is 4x, and then add that 4 to both sides to cancel out that negative 4, and you get 4x equals 4, which means x equals 1. There is one of our critical points. However, we basically missed one here. The other thing we could do, you have to be careful because we have this denominator here where x could be 0. Essentially what we're saying is we can't plug in 0 for x. 0 won't work. So that's going to be one of our points where it breaks it. In other words, we also have to pay attention to having no derivatives, so or undefined derivative. Okay, and so that occurs, and it occurs when 3x to the 2/3 equals 0, because we can't divide by 0. That's this part right here. It's that denominator. We can't have that be 0, and that occurs when x equals 0. If x equals 0, 3x to the 2/3 is going to be 0, and so these are the points we are interested in looking at. All right, so there we go. There's part A. On what open intervals of f increasing or decreasing? So our open intervals we need to look at are dealing with these 2 points, this one and this one. All right, so if we like drew these on a number line, we'd be here at 0 and then here at 1. And so our intervals would be from negative infinity to that 0. So that's this interval here. Then we'd have this interval here from 0 to 1. And then we'd have this interval here from 1 to infinity. So those are our 3 intervals we need to look at. So let's look at negative infinity to 0 first, that open interval. And when we look at that one, we can do the derivative f prime of something to the left. So just to make this simple, let's just do -1. In fact, I don't even really need to work out the whole problem. All I really need to do is take a look at what's going on with the signs of these things. And I mean, you can plug it in if you really want to, but you don't necessarily have to plug it in. So if I combine these together, right? If I take, let's just do a little shortcut here. Let's make this right here. If I multiply this over here by 3x to the 2/3 over 3x to the 2/3, I can have them have a common denominator, and I can actually combine these into the function 4x minus 4 over 3x to the 2/3, all right? Because this would be x to the 1/3 times 3x to the 2/3 is just 3x, like we did before, and we'd have 3x plus x, that's our 4x, minus 4, and then they have that common denominator of 3x to the 2/3. So I can look at this right here to determine this. So if I plug in -1, in the numerator, I get -4, minus 4. So that's going to end up giving me a 0 value. So maybe we want to try something like -2. If I plug in -2, what do I get? I get -8. And then after that, I get, so I get -8 over, and then -2 to the 2/3. Well, that's 2 squared, so that's a 4, and then a cube root of it. That's going to give me something positive. So I end up, essentially, I don't have to know the exact number. All I really have to do is pay attention to that. I ended up with something negative divided by something positive, and that gives me something negative. And so here, I know that I have negative slopes, and therefore, during that interval, it's decreasing, okay? If we take a look at the next interval, from 0 to 1, I can pick a point in there. Let's say we pick between 0 and 1, we might as well do 0.5. So f prime of 0.5. If we look at that one, if you plug in a half times a 4, that gives us something smaller than 4. That gives us a negative in the numerator. And in the denominator, we get a half to the 2/3 power. That is going to give us a half squared, which is a quarter. And then the cube root of a quarter, we're just basically, we're ending up with something positive again. There's nothing that 2/3 can do to change the sign of a number we plug into it. So something to the 2/3 power, because you end up squaring it, is going to be positive. So if it's positive, it's positive. If it's negative, it's going to be positive as well. So anyway, this is a negative or a positive. This is also a negative slope, and therefore this is a decreasing section as well. So now we just need to look at this last section, which is 1 to infinity. And from 1 to infinity, we just pick a number that is greater than 1. So let's say 2, f prime of 2. And if we look at that, in the numerator, we get 2 times 4, that's 8. 8 minus 4, this is a positive numerator. And as we just said a minute ago, the numerator, if we plug a positive and you take it to the 2/3 power, it's still positive. So this is positive over positive. This is a positive slope area. Therefore, this is an increasing area. The function is increasing on that interval, okay? And so the next part says, at what points, if any, does f assume local maximum or minimum? Well, if we look at the point for 0, so in other words, if we look at this point right here, we see that we're decreasing to decreasing. So it's decreasing to decreasing. That is not a change in the slope, and therefore this is not a maximum or minimum. However, if we look at this point 1, 0, we see we go from decreasing to increasing. That means we had to have been going down and then started going back up. That makes the point with x equal to 1, that makes that a minimum. It's a minimum. Okay, and if we come down here and we see here's our graph, we look at x equals 0 right there, and it's decreasing and then decreasing, and you notice that is not a maximum or minimum, it's not an extreme value. But at x equals -1, we end up at 1, -3. We are decreasing and then increasing, and we are standing basically down in the bottom of a valley. All right, we're like down in the hole there, where either direction we walk, we would be going uphill. So that right there tells us we have that. And then what are the values of the local extreme? Well, they're right there on the graph. You could just, you just simply have to plug them back in, right? So if you wanted to do part D, you would just plug in the value of x. You just do f of 1. And what was our function? X to the 1/3. So that's 1 to the 1/3 times 1 minus 4. And 1 to the 1/3 is 1. 1 minus 4 is -3. So at x equals 1, we have a value of -3. Okay? And that's what we see right there in the graph. All right, so that's it. Go ahead, try this example, and then do the next two, and then take a look in the notes. They should be pretty similar. Take a look in the notes and see if you can figure, if you did figure them out, if you got the right answers, okay? And I'll put the answers in the notes for you to take a look at. All right, that's it. Thank you.